You count x, counting x can be hard. What should we do? Then we count y. What's y? If x, y have a bijection, what's bijection? Injection and surjection. Every x go to a y, that means everybody A, B, C, D will shoot something. And then surjection, every y is shooted by something. Then if you have these two sentences, you have bijection, 1 to 1. This 1 to 1 is the powerful thing. That means that everywhere, no matter how I count y, there will be a corresponding thing in x. So if counting x is hard, then count y. There's no free lunch. You have to sacrifice something. The sacrifice is to draw this line. This method requires you to find a bijection. If you find a bijection and you can construct a y, and y is very easy to count, then you count y. You don't need to count x. This is the idea. And actually, this is exactly why we learn binomial. Why? Binomial is just n factorial divided by something, which is just some calculation and easy to do. But the coefficient of the binomial is exactly a bijection argument. Why we study binomial? Because the coefficient of this thing is exactly this thing. So this is my y. Counting what? Our combination of an n set, this is the x. Okay? It's hard if we do all the argument from first principle. So we use some formula or some equation to help us counting. The working principle is because they are 1 to 1. So now I'm going to give you one example telling you this is very powerful. There is something called rising number. What does it mean? Digit is rising. For example, 1, 2, 3 is getting bigger, the digit. So yes, it's a rising number. 3, 4, 3 is no, because after 4, you go down. So this is not rising. 2, 3, 3, 4 is no, because I don't allow equal. So 3, 3 do not change, is no. 1 itself is a rising number, okay? So then the question will be, how many 3-digit rising number are possible? That means 1, 2, 3, 1, 2, 4, 1, 2, 5, 1, 2, 6 are rising number. 2, 3, 4, 2, 3, 5 are all the same. How do you solve this problem? This is what? This is the set x, something hard to count. So let's draw a tree. 3 unknown, D1, D2, D3. Start with first guy, D1. How many branches? The first one is 1. And then the second one is 2. And then 3. And then 4. And so on. So you have so many cases. D1, D2, D3 up to what? D9. And if D1 is 1, then you will have what? Another branches, 2, 3, 4, and so on. And then for each digit, you have another tree and branch and so on. So then for D1, you have how many cases? 28. By what? Counting this tree plus this tree plus this tree plus until the end. Very tedious. And then for D2, you need to do the same thing. D3, D4 until D9. D9 is impossible because for rising number, nothing after 9. So nothing on 9. And you count 84. So that means what? Counting x by 3, very tedious. Now we have to make a y. The hard part in this technique is how do you come up with a y and how do you come up with this? This is the hard part. And once you trade off, you sacrifice doing something difficult here, counting y is very easy. So you count this and you have a number 84. Oh my gosh. Here's how you count bijection. So you need to realize the following two things. This is the hard part. Fact 1, if D1 smaller than D2 smaller than 3, 3 means D1 not equal to D2 equal to 3, trivial, right? Then fact 2, if they are not the same, there's only exactly one rising number. That means what? If D1, D2, D3 is a rising number, I have this arrow. This is fact 1. What's fact 2? Fact 2 is saying that if I have D1, D2, D3 not equal, I go back, I have, this is fact 2. Then there is a bijection. What? I said bijection means one way from x to y. Same as one way from y to x. Count x is hard. Okay, we count y. I just show you that the two arrows. So that means what? We should count what? How many D1, D2, D3 are different. So therefore, counting rising number is the same as counting how many ways we select 3 different digits from 9 symbol. Done. This is how you count by using x. You have to think about a crazy tree, very tedious. Now I use the y. Y is just 9 choose 3. And you solve this thing less than 10 seconds. But come up with this is very difficult. So this is the technique. The technique is, let me repeat, sometimes counting x very difficult, so you count y. The trade-off is, counting y very easy, but getting from x to y is very difficult. There's no free lunch. You either spend a lot of effort on counting x, or you spend a lot of effort on making this connection. Choose one. So this is the idea about bijection. And then there are more examples. So for example, I will talk about, let's say, this one. How many 4-digit rising number, but the last digit has to be 9. And because 9 is chosen, then 8 chose 3. Done. And this is 4-digit rising number, right? If you use the tree argument, your tree will be crazily big. And then here's another example. Suppose now it's not 0 to 9, it's A, B, C, D, E, F, G. How many 5-letter rising string with D2 is D and D3 is F are possible? That means I actually have a string like question mark, DF, question mark. Then, in this case, how many possible for the first question mark? Everything before D, so A, B, C, right? So you have 3. And then, what about the letter? Every letter after the F, that means G, H, I, J, okay? So you have this. The first way, you have 3, because it's 3, choose 1. The last one, you have this number, okay, 20, choose 2, so done. A city have 10 intersections. Some of them have traffic light, and some of those with traffic light have a gas station. How many ways can this happen? So I have A, B, C. A is no traffic light, B is traffic light only, C is traffic light with gas station. That means what? That means this English sentence is my X. This set is my Y. So instead of solving X, I consider this set, and I count on this set. I talked about it last time. It's just 3 to the power 10. So this is an example of what? Of establishing the connection here. So to use counting by bijection, you have your original problem. You need to create something from nothing. That is the Y. That this Y has to agree with X in a one-to-one sense. And if you can do that, then you can count Y. And here's a fancy figure. How many possible string 3-digit of binary number? That means, computer, you have a bunch of 0, 1. So these are all length 3 string, 3 bits, called 3 bits. You have this picture. This is what? This picture is how many ways you can sum something to get 4. You have this picture. What is this? This is called tiling. Okay, ignore this for a moment. So you can think of all these 3 pictures. They have the same structure. What does it mean? It means counting how many possible ways to have a length 3 bit is the same as counting how many possible ways to have number add up to 4. So, in other words, they are a bijection. The content inside are different. The content inside, this is a 111, this is a number 4. But these are what? These are just symbols. We don't care. We care about the structure. So, if counting like this is the same as counting like this, that means the method you use to count either one of them can be used to count the other guy. And this is the part that makes combinatorics hard, because we don't really care about what is inside. We care about their structure. Okay? And then this one is a table called 12 4-way. There are many things you need to count. This table summarizes most of them. And you just need to know those that have a number. You actually have 3 things. You have ball and you have box. You throw ball into a box. So you will have rule on ball and box. And then you also have the rule on what? Here is written as F. F means how you throw a ball. Because what is F? Okay, you should learn this in set. If I have an arrow pointing from X to Y, this is a function F with domain X mapping to codomain Y, right? So this kind of arrow is a F. And then for F, you can have injective and surjective. So that means here, I have 3 sets of rules. Number 1, a rule on the balls, rules on the box, and a rule on the F. So this is the idea. Ignore the fancy names, orbit, that kind of thing, or abstract algebra thing. You don't need to worry about. Look at the wording. It explains. Algebraic combinatorics. So remember, we talked about this in lecture 1. We see that these 2 numbers are the same set of numbers. Why? Now you should know, because they have a bijection. This kind of thing, in the inclusion-exclusion principle, is a counting structure. It's a X. Just by chance, the binomial coefficient is a Y. And they have a bijection. So that's why we can use binomial to count stuff. Then what's the generalization? If we want to count permutation, combination, whatever thing, can we always get a Y to count the X? Yes. So here's the starting point. Suppose you have ABC in Z, that means an integer. 2, 5 bounding A, so A is what? 2, 3, 4, 5. What about B? B is 3, 4, 5, 6. What is C? C is 4, 5, 6, 7. And I'm asking you, how many possible ways A plus B plus C is 17? If you do not study binomial, bijection, if you want to solve this, you have to draw a tree. This tree will be crazily big. Now I'm telling you, what's the bijection? The bijection is the coefficient, this is the expression, coefficient of x17 of this guy. That means you write down this, you do the math, Find the coefficient of x17 in this, you solve the problem. Why? Because bijection. I'll explain the why later, but now I'm telling you it is a bijection. Second one, you have 8 cookies. They are identical. That means, in this case, identical means there's no order. That means it's combination, not permutation. Okay? And you distribute among 3 kids. Each children get at least 2, but no more than 4. How many ways can you distribute the cookie? The answer is the power x power 8, and then you find the coefficient of this in this expansion. You will ask why? Bijection. This works. Okay? Because it's a bijection. And now I'm telling you what the heck is this. This term means first children get 2 cookies. This term means first children get 3 cookies. This term means first children get 4 cookies. In other words, the power of the x has something to do on counting. This is first children. Product rule with second children. Product rule with third children. So multiplying bracket is product rule in counting. Summation is sum rule in counting. So in other words, 2 plus 2 primary school. Yes, now this plus has a meaning. It's sum rule. 2 plus 2 times 5 primary school. But this multiplication has a meaning. Everything I said, even a line like this, has a meaning. Please understand the meaning. This is sum rule. This is product rule. So this is now something extra. This kind of problem is called restricted partition. That means what? I want to split 17 into A, B, C, but with this constraint, restriction. If there is no restriction, then I remove the word restricted. It is a partition. Pn means how many ways you can split n into a sum with non-negative integer. Let me tell you. You may know permutation, combination, arrangement, repetition. Why didn't I talk about partition? Because partition is a Nobel Prize level problem. This picture is the partition of all the possible number, small number. And nobody knows what's the closed form formula. What the heck is this? So suppose you have only one thing. How many ways can you split one? One. Okay? Suppose you have 2 things. How many ways can you partition 2? You either have 1 plus 1. Think about vertically means 2 types. And horizontal means you take all. So you have 1, 1, or 2, right? So you have 2 ways. How many ways can you split 3 things? You can have 2 plus 1, 1, 1, 1, and 3. So 3. How many ways can you split 4? You have 5, and then 7, and 11, 15, 22, 30. Okay, what is the formula of this? Okay, fused metal level. Nobody knows what the P5000 looks like. Nobody knows. That's why we don't usually talk about partition of Pn. We talk about partition under some restriction. Because this problem is very difficult. So this is, I just let you know, this is a very tough problem. Just split some number, and we don't know how to count them. This is not in exam, I just let you know. Now I'm going back to the algebraic combinatorics, and I'm telling you the magic thing. So, suppose we have 6-sided die. Suppose you toss 2 die. This figure are 36, right? 6 times 6, 36 possible case. Now I'm showing you some x in the bottom. What is this? So I have x1 plus x2 plus up to x power 6. And then I multiply them. This is the table. All the possible x1 multiply other x, right? And then you know x1 is give you x squared. x6, x3 give you x9. Okay, so I get this table. How many x squared are there? 1. So 1. How many x power 3 are there? 2. So 2. How many x power 7 there? 1, 2, 3, 4, 5, 6. 6. So you get this. Now I'm telling you, this 1, 2, 3, 4, 5, 6, 5, 4, 3, 2, 1 have some special meaning. This means how many ways you can toss 2 die. The sum is 10. You have 3 ways. How? 6, 4, 5, 5, 4, 6. 3, right? 3. And suddenly, let's say, I have the same dice, but due to some reason, 1 is impossible. 1 will never occur. Then I can say, this picture, I ignore all the 1. So I can just hide all the 1. Here, I have all the possible x combined, right? Now, 1 is impossible. It's same as the coefficient next to x1 is 0. So this guy die, this guy die. I just need to say, this guy does not exist. This guy does not exist. So now I have this part. How many x to power 8 are possible? 1, 2, 3, 4, 5. So 5 raised to power 8. In this special dice, how many ways I can toss such that the sum is 8? So 1, 2, 3, 4, 5. 5 way. 5 way. You see, multiplying polynomial suddenly give you something about counting. This is the cookie question. How to distribute a cookie to 2 children? That what? At least 1 cookie for each children and no more than 6 cookies. So that means what? Children 1 is the first x, children 2 is the second x. This means children 1 get 2 cookie, children 2 get 6 cookie. This means what? Children 1 get 3, children 2 get 5, and then children 1 get 4, children 2 get 4, blah, 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 and so on. And if you multiply their power, they all get 8, 8, 8, 8. Yeah, you are distributing 8. You throw 8 cookie to them. Now, how many we distribute 7 cookie to 2 children, and at least 2, no more than 5? So it's the same as this get 2, this one get 5, this is at the limit, and you flip it, and these are all the possible cases. x7, 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 x7. So that means what? This is the same as you multiply these two and find the coefficient of x7. Oh, I shall show you this one in lecture 1. Now you understand. I show you in lecture 1 there's a reason. This example, second example, third example, fourth example, fifth example, 6, 7. I show you 7 examples. This is the 8th example. Now you should have a feeling, okay, multiplying polynomial and counting have some black magic working in the background. Another example, A, B, C sum to 17. With A, this, B, this, C, this, the answer is the coefficient x17 of this polynomial. And if you count them, it will be 3. And this is how you solve. That means what? This is the same as, okay, imagine I have this problem. You can think of this as the A space. This is the A space. This is the B space. And this is the C space. In this 3D plane, there will be some dot representing what are the combination of A, B, C that sum to 17. And you are actually trying to find where the location of that particular dot is. For example, this dot at this point, for this x, y, z coordinate, give you 17. Then this is a dot that solve this. And you are trying to find their location. This is the geometric understanding. So now I'm going to talk about the math. This kind of thing have a name called power series. What is that? You have something plus something times x power 1, something plus x power 2, plus to infinity. Important, to infinity. We don't stop in the middle. These kind of A0, A1, A2, A3, A4, A5 are called coefficient. And here are an example. Consider one set. That means only have one thing, one object, one element. Element start with E, so I call it E1. How many ways to select nothing? You have one way to do nothing. How many ways to select one thing? Your whole set have only one object, so one way. So you have one way to do nothing, and one way to do one selection. Can you pick 2 things? No. So 0. This thing is an English word. This is an equation. The color corresponds. So this is a generating function or power series of selecting one thing from one set. So in other words, what is this? This is a very innocent 1 plus x. But it means how many ways to select empty set and how many ways to select one thing. There is a 1 here hiding in the background. There is the 1 here have a x0 hiding in the background. And this 1, this x, right? There's a 1, right? There is also a 1 there hiding here. So what I'm saying is that this 1 plus x secondary school. But this 1 has a meaning. This 0 has a meaning. This 1 has a meaning. This 1 also has a meaning. Even this plus has a meaning. So you see, now something very innocent suddenly have lots of meaning. And if you understand all the meaning, you know how to do counting. This is easy, right? What about this? You have a set of 2 objects, E1 and E2, element 1, element 2. How many ways to do nothing? 1 way. So this means number of ways you select 0 element. How many ways to select 1 element? You either select E1 or you select E2, and that's it. So 2 ways to select 1 element. How many ways to select 2 elements? We are talking about combination, so E1, E2. So 1 way, there's a 1 here. How many ways you pick 3 things? Nothing you can do. 0, 0, 0, 0. Get this? So 1 plus 2x plus x squared. Wow, it's 1 plus x squared, right? You know, 1 plus x whole thing square, right? Okay. This has a meaning. It means this. And more importantly, okay, this is this, right? What is 1 plus x? 1 plus x is how many ways you can do selection in one set, right? This dot is a product rule, right? What's product rule? Select 1 from P and select 1 from Q is the same as select 1 from Cartesian product PQ. This is saying select 1 from Cartesian product PQ. This is select one thing from set P. This is select 1 from Q. This dot means select 1 from P and Q is this, and they are all equal. Furthermore, what is this? This is exactly binomial coefficient. Now everything goes together. That means what? The x to a power, I call it P. There's a coefficient, there's a C. This expression has a meaning. This means there are C ways to select P number of x. So this thing, you have 3 representation. This is called generating function or power series. Or you are lazy. It said, I don't care about the x. I just write the coefficient. So you have 1, 1, 1, 1, 1. I draw this. 1, 1, 1, 1, 1. And then, or you can draw this called function or recursion. I said my fn is 1 for n is 1, 2, 3, 4, 5, 0 otherwise. So you have 3 ways to represent this kind of thing. These 3 kind of things are the same thing. Okay, again, these are same thing. It's just different way to look at this. And then, for example, what is this? X plus 2x squared plus 3x cubed. There's no x power 0, right? So we have 0, 1, 2, 3. What about this? 0, 1, 0, 1, 0, 1, 0, 1, 0, 1 is same as all the odd power add up together. Then what about 1, 0, 1, 0, 1, 0, 1, 0? All the even power. Be careful, we start with 0, okay? X power 0. Here's a first example. Suppose I have prefix, vowel, suffix. How many possible English words? These are not English words, some words, okay? You have set, sit, tactic, blah, 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 okay? And then what? If you count this, you have 27 outcome. Now I'm asking you, how many length 5 words are there? So if you want to do it by brute force, okay, 1, 2, 3, 4, 5. So quack, quick, whatever thing, these are length 5. This is not, okay, so I have to stop in somewhere in the middle, okay? 1, 2, 3, 4, 5, 6. So this one is not, okay? This one is also not. So this number, there are 9 of them, 9 length 5 string. Now let me do power series. So suppose QST is among the first object, so I put like this. This means what? This means I select QU, or I select S, or I select T. This plus is what? Inclusion exclusion principle with an OR. Do you remember? OR. So the OR is a plus. And then in intersection, it's like multiplication, right? So it's a dot. So there is a multiplication. This means what? I select from here, and I select from here, which is select from vowel. And then I also select from suffix. So I have this. Now I don't care about what's inside. I just write down this as x. I have this. And x is x, 2x. Okay, this is 2x. These two sum up give me 2x. This give me x squared. Okay. This is what? 2x and x squared. This is what? X and 2x squared. So I'll have this. Now I calculate the expansion. It gives me this expression. I want length 5 word. The coefficient of x5 is 9. It's exactly 9. You now should get the idea. Throw away all the n choose k, whatever choose k, rising, falling polynomial. Always work with this. This is the best. Yes. So basically today we are talking about how to count stuff using this. This is the example. The idea is the following. This kind of thing has a name called generating function. What does generating means? Generating means the following. This expression looks very innocent. Let me tell you. This expression, just a math equation, is 6 sentences. What 6 sentences? First sentence, there are 1 way you to select nothing. Second sentence, there are 1 way to select 1 thing. Third sentence, there are 1 way you select 2 things. Fourth sentence, there are 1 way select 3 things. Fifth sentence, there are 1 way select 4 things. And lastly, the 6th sentence, 1 way select 5 things. So this thing is 4 sentences. 0 way to select nothing. 1 way select 1 thing. 2 way select 2 things. 3 way select 3 things. And that means if we count things by this kind of summary, you can talk about summary, then suddenly counting becomes very easy. You just multiply this x, y, z, and then find their coefficient. So this kind of thing has a name called generating function. Generating means it generates all the possible ways we can count things. And if I have ax be the gen function for selecting stuff from a set A, and if I have bx for the gen function that selects stuff from set B, what are the possible ways to select both A and B is product rule, but generating function version is just multiply there. What about inclusion exclusion principle? Yeah, you just do this. What about sum rule? Yeah, you just do this. So select from A or B is the same as this. Select of A and B is this. Select of A or B, inclusion exclusion, that means you have to subtract the intersection is this. Then what? You can do the same for permutation, permutation with repetition, combination with repetition, and what? Falling, factorial, rising, factorial, even, Stirling number, or a crazy number. Yes. So this is the idea. Product rule is just AX, BX. Sum rule is just AX plus BX. Inclusion, exclusion principle is just the math. Division rule is the same. So that means multinomial is just something like this. And then, okay, permutation is, we know permutation is n factorial, right? Why? Because this is the generating function called exponential generating function. And I said the coefficient next to the x are the what? The number of ways to count stuff, right? So now this guy is the number of ways to count stuff. But if I want this to be my function, then this guy have to agree, and this will be the k factorial, which is the permutation. Okay, this one later, but I just let you know. And then what? Generalized permutation will be something like this. That means I have something, a bracket. Okay, this is multiplication. So I have a 1 here, and then let's say I have 1 minus x 2, and then let's say 1 minus x 3, and then so on. This means what? If I expand this expansion, I will have a big polynomial in the denominator, and I simplify all the math. The coefficient will tell me, oh, this is the number of ways, what? Suppose all the power sum to 10, and this is 2, this is 3, this is 4, is the same as you have 10 people, go to chess, and then how many possible ordering can you have the champions, first one up, second one up, according to the fact? So 2 from US, 3 from UK, something like this. Yeah, is this polynomial? And then you can do the same thing for this. And then ddx also have a meaning. Okay, I know some of you didn't know calculus, didn't study calculus in the past. So when I talk about these three, I will make sure explain more. This means differentiation, and you make power go down by 1. I will have an example on this later. This makes you differentiate this 2 times. This means you do the opposite of this. So now, for those who know calculus, now I'm telling you, this have meaning. It means you count something with 1 distinguished element. This means you count something with 2 distinct elements. This means you count something by accumulating them. And even log have a meaning. Log means you count things by connected stuff. Yeah. So now you see, you should view everything with a new perspective. Why? Because I told you, even a plus sign have a meaning. Even the horizontal line have a meaning. Then of course, these kind of things are going to have meaning. There's something in behind. What are the things behind? Hypergeometric sequence. I told you yesterday, hypergeometric sequence is everything. And since hypergeometric sequence count everything, and every function can be written down as a hypergeometric sequence, so every symbol has a counting meaning. Okay? But again, let me say, hypergeometric sequence is not in exam. I just let you know. And I just demonstrate to you the power of hypergeometric sequence. This kind of thing is just special case of hypergeometric sequence. And I just tell you one specific subtype here. And you see immediately it's extremely powerful in counting things. That's the why I talk about hypergeometric sequence. If you know how to do hypergeometric sequence, literally you can count any crazy thing. Okay, now, I will stop here and see you Friday.